Boom. Okay, so want to cover a couple of things today. Much of what we talk about today will be valuable for the exercise or for the assignment, assignment 2, and others will be important for sort of helping to recognize some features of this. Differences between the sorts of modeling we've been discussing. On the one hand, agent-based modeling, on the other hand, system dynamics modeling. Okay, so I had a take-home exercise which I had asked you to pursue, and this had several pieces, and I'd like to briefly go over those pieces. So within this take-home exercise, we had modified a model that was previously built in class. You may remember this model where we had individuals represented in this fashion, susceptible and afflicted states, and they had a fixed rate going from one to the other given by the affliction hazard. And I argued that the hazard is a rate. It's not a probability. It can be greater than 1. If it were 2, how long would they spend in this state on average? This hazard were 2, how long would they spend in here before leaving on average?
Half a year.
Half a year, 1 over that hazard rate. If its value is 1, they spend about 1 year there on average. If the rate is 0.1, they spend 10 years there on average. So the amount of time they spend in here is 1 over the rate. We saw that with system dynamics, right? Remember, we could talk about there was a parameter mean time in this state, and if so, we'd have a flow out if we had some mean time and some stock. Remember, this is with system dynamics, right? And this was some mean time, call it tau, and this stock is x. What's the formula for this in system dynamics? What was it? X times tau? This is tau. This is an amount of time, an average time that they spend in the stock. What's the formula for that?
1 over tau.
Yeah, so it's x over tau. And alternatively, you could specify it as x, and here's a flow out with a valve here, and this is alpha, and this is a hazard rate, and your formula is what? X times alpha, good. So here, tau, the amount of time that you spend in this state, and alpha are related in a simple way. What is that way that those two are related? Alpha or tau. We could phrase a given situation as either this or this. So how could I specify alpha in terms of tau?
Inverse.
Yeah, it's alpha equals 1 over tau. So if we multiply by alpha, it's the same as dividing by tau, right? Multiplying by alpha is the same as dividing by tau. You can just flip it around and you'll get tau equals what? 1 over alpha. And that's all we're seeing here, ladies and gentlemen. Tau is the mean time you spend in this stock is 1 over the hazard rate, 1 over this chance per unit time, and that's what we have here. Okay. Now, I tried to show, and I'm not going to go revisit it in full, but I did a little demonstration of the fact that if you have a chance per unit time of going, of leaving, and we only consider it once, a chance per unit time of leaving, and we only consider sort of one try at it, you're going to have a probability of remaining of one thing, and then as we consider more and more tries, we divide it up q over 2 to leave and q over 2 to leave, and then divide it up further, and we eventually got to q over n to leave, and we're considering it n times here. We had a probability of remaining here. If you have a chance per unit time of leaving of q, here you have a chance per unit time of leaving of 1 minus q2 squared. and this is a chance of remaining, right? This is 1 minus q, yeah. And then this was 1 over q to the n. My point in doing this was to communicate, this is n, my point in doing this was to communicate that you can have a chance per unit time, say of q, of leaving. If you only consider it once, you get one suggestion for your chance of remaining. This is the chance remaining if you have 2 kicks of the can. Here, if you have n kicks of the can. And as we consider very, very, very small intervals, very, very small intervals, and lots of them, this goes to what limit? E to the minus q, okay? And I argued last time that your probability of remaining here in the susceptible state, just like the number of people who remain in this state as time goes to infinity, they go down as e to the minus epsilon, or alpha times t. And that is just an example for t equals 1, okay? So the point is, this hazard, it can be greater than 2 because it's not a probability, it's a probability per unit time. So you consider very, very small intervals, and you ask, do I go in that interval? Do I go in that interval? The chance of leaving in a given interval, if you have a hazard rate of alpha and you have a very small interval of unit of size delta t, the chance of leaving in that small interval is this. And so you may have a hazard rate of 2 on a per day basis, and your chance of leaving within a given hour is then approximately 2 times 1 over, or 2 times 2 over 24. So it's 2 divided by 12. So that's delta t here is 1 hour, so it's 1/24 of a day. And you're multiplying it times this hazard rate to get the approximately probability per hour. But we can actually do this as finely as necessary, and this is what pops out. If we have that situation, this is what pops out. We get a probability of remaining there of e to the minus alpha t, alpha times t, and that is what we see at this level, and it's what we see here with these stocks, okay? That's the number of people remaining. And just to remind you of what that looks like intuitively, we saw it from early on, at a high level. But here we have this model, and it depicts. This is a hybrid model. It includes system dynamics and agent-based features. Here we have a transition between these two. Here's the hazard rate, and then we have individuals who are in this population who are transitioning according to this, with a certain hazard rate. And if we run that, what will we see? What will we see popping out? Will they be similar or not similar?
They'll be pretty much the same.
Similar, dissimilar. Pretty much the same. Why is there any variation whatsoever?
You're working with individuals and agent-based, so you can have little variances over smaller time.
Yeah, and what's really going on? So beautiful. Thank you very much, Andrew. That's right. And why is there variance with individuals? Here's person 1, person 2, person 3, etc. If we go far enough, we'll find someone who's still susceptible. Why is that? It's because what comes into the equation here that does not come into the equation with that, does not come into the equation with this. What is going on at that individual level that's different? What's going on here?
Every individual is calculating their chance to leave separately.
Yes, and the chance is something that is stochastic. And when I say stochastic, I mean it involves uncertainty over time. This class is about dynamics. It's about change over time. And this is uncertainty over time. Okay? Stochastics. So that's what's present here that is not present in the original model. So if we go up in the system dynamics model, the aggregate model, this admits no uncertainty. And in fact, you even see that the number of people susceptible is coming down here in a continuous fashion. It's not dealing with the quantized nature of people, that either a person's in there or out. Here's 18.315 people remaining. But if we look at this close enough, we will see that even though it follows very well this sort of situation, there's these slight variations in it due to stochastics. And that's a difference between the two models. Okay, so I asked you as part of this take-home exercise, which I understand is formally due in class tomorrow. I'm not sure how long our lecture will be tomorrow, but I don't think it will be long. But you're welcome to hand it in until tomorrow. I'm hoisted on my own petard on that one. Let's go. I asked you to change this. This has a mean time in this state of what? What's the mean time in this state? 1 over this affliction hazard. That's how long they spend there on average. So I asked you to change it to a timeout, but in a way that preserved that mean time. So it's now a timeout. You leave in exactly an amount of time, but the amount of time in which you leave is different for each person. They come in here, and this value is determined. It draws from a uniform distribution whose minimum value is 0, and whose maximum value is twice 1 over that hazard. This is uniform distribution. So here we are. Here's our uniform distribution. And it goes from 0. Oh, that looks like a misshapen thing. Okay, 0 to 1 over alpha. I'm calling this is the affliction hazard. Okay, sorry, twice. 2 times that. Okay, 2 times that. So what's the average value of this, or what's the mean value of this? 1 over alpha, yeah, right. It's right in the middle, right? 0 to 2, you're equally likely to fall anywhere in there. So the average value is 1 over alpha. The average amount of time till you leave. But the question I posed to you then, and the question I pose to you now, is does this give the same results? Why not? Why not? Correct, it does not give the same results. And let's reason about why. Why not? How is it different? Anyone want to predict before I run it flat out?
Straight line.
Yeah, essentially a straight line. Almost exactly a straight line. So what's going on there? Why? Essentially everyone gets afflicted by time 100. And if we look at what the affliction hazard is, it's 0.02. Can anyone connect those 2 points?
The maximum value or affliction hazard is time out, or the amount of time divided by the affliction hazard is the maximum affliction hazard is.
Okay. Okay, so let's think about the affliction hazard of 0.02. What's 1 over 0.02? 50. 50. And what's twice 50? 100. Okay, so the person who's going to stay there the longest in the state is going to stay for 100 time units, 100 years. The others are going to be leaving in as short as 0 years. Now, even though the average is retained, even though the average is invariant, even though the average is the same for a rate transition, the result is very, very different. We have no one who stays for longer than 100 years at all. Whereas in the original rate formulation, there are some people who have very, 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 very long sort of times, long tenures in that stock. But most have very short tenures. So, ladies and gentlemen, this is the number of susceptible here who remain. You'll notice that with the rate formulation, a lot of people come earlier, but some people come much, much later. By contrast, even though it has the same average time, this other formulation with a timeout yields much more contained, much more limited variability. So it's not just the average that matters. It's not just the average that matters, ladies and gentlemen. It's also the distribution. And here we had the luxury of imposing a distribution on how long they've spent there. Could we do this in aggregate system dynamics? Could we specify exactly how long they spend in one of these stocks? Could we impose a distribution? Yes or no? How would we impose a distribution for how long they spend there?
I think another parameter.
Well, okay, so
It would just be a flat rate. Would it be 1 over reflection hazard?
okay, so I'm hearing different ideas, which I welcome. Let me make another comment on it, ladies and gentlemen. This, if we go back to the original formulation with this formulation, where they have a certain chance per unit time of leaving here, is a very special formulation. It's special formulation in that it is what we call, well, you tell me. I could tell you, but you tell me. So, ladies and gentlemen, how does your chance per unit of time to leave change as we stay more time in this state? So suppose we've been in this state we've just come in, versus we've been here for 10 years, versus we've been here for 100 years. What's your chance of leaving per unit time?
The longer you stay, the higher the chance of living.
Okay, so I'd like to refine that. I'd like to take that statement and poke at it a little bit. I won't poke at you. Don't worry. So ladies and gentlemen, when I say what's your chance of leaving, I'm being pretty imprecise. Let me sharpen that a bit. How, if I just came in versus I've been here for 10 years versus I've been here for 100 years, how does my chance of leaving in the next year change? It doesn't change. It's always as given by this hazard rate. Okay? I always have that same chance per unit time of leaving. Now, put another way, my probability, if I want to turn it as a probability of leaving in the next year is, well, this is my probability to remain in the next year. So it's going to be a probability of this, of leaving in the next year, it turns out, okay? Which e to the minus 1 minus e to the alpha of leaving the next year, which not coincidentally is directly related to that. That's my chance of remaining in the next year. The chance of leaving in the next year is 1 minus that. So this is my chance of leaving in the next year, my probability of leaving my next year. My hazard rate is the same. If no matter whether I've stayed there 1 year, 10 years, 100 years, 1 minute, my chance of leaving in the next time unit, whether you consider, chance of leaving in the next minute. If I've been there 1 year, it's the same chance for leaving in the next minute for 10 years, same chance for leaving in the next minute for if I've stayed there 100 years. It's the same. And we call this situation, ladies and gentlemen, based on that, a memoryless process. It doesn't care when you came in. It doesn't care about your history. If you are in this state, that state summarizes everything you need to know. It's memoryless. It doesn't care about where you came from, when you came in. You have that same chance per unit time of leaving. Okay. By contrast, I'd like you to take a look at this situation. Same average time, this uniform distribution. Is this memoryless? No. It is most emphatically not memoryless. Does it matter when you came in to determine when you leave?
Yes.
In a big way. I would argue you never stay longer than 100 years here. So if you've been here for 100 years, you're certain to leave in the next time unit. If you've been here 0 years, you are less likely to leave in that next little bit of time. And in general, if maybe it's more clear if we said this. If this were a timeout of, let's take it to its logical extreme. If this were a timeout of exactly this amount of time, 1 over that, the mean is the same. The average is the same. You're there on average for 1 over alpha time. Is this memoryless? No, it's memory full. It's about as memory full as you can get. Right? You have 0 chance of leaving in the first little bit of time, but once you're there for exactly this amount of time, you will leave. It's memory full. It cares totally about how long you've been there. Probably, maybe someone could close the doors, because probably they don't care totally about the course contents. I'm out there. Ladies and gentlemen, so I'm told my voice penetrates these walls yet, but I'll try not to do so. Okay. It's like the sound of a electric guitar or a bagpipe. It penetrates the walls in the most unseemly fashion. Okay, so ladies and gentlemen, that's the average amount of time is that. And you leave, and this is totally memory full. So we have memory less and memory full. And in system dynamics, coming back to our question, and leaving behind the bagpipes, we have only an ability to characterize things in terms of these. Each stock is memoryless, ladies and gentlemen. Each stock is memoryless. It's considered well mixed. It doesn't matter how long you have spent in that stock. Your chance per unit time of leaving the next time unit is the same. This stock is considered homogeneous. That's another way to put it. It's considered, your chance of leaving in the next little unit of time is considered to be the same, no matter when you came in there. As long as you're in there, that totally summarizes your situation as far as the model is concerned and your chance per unit time is leaving. So all stocks in system dynamics are associated with an exponentially distributed residence time. In other words, the amount of time you spend there is drawn conceptually from an exponential distribution. You have the same chance per unit time no matter how long you've spent there. In classic system dynamics. Now, some system dynamics packages allow you to treat it as a conveyor, it's called, and you will leave after a certain amount of time. But it gets pretty awkward to deal with those things, and in traditional system dynamics, you're adhering to these memoryless situations. So if you want a different distribution to be imposed, what you do is you break that stock up into pieces. You create what's called an aging chain, or a higher order delay, where you stack one after the other, and you can shape the distribution that way. Here, in agent-based modeling, we can pick the distribution explicitly. I want to draw attention to that. Here, we replace this like that, but alas, here I drew it from uniform distribution. If you go up here, and you can do it, but I can't probably. Do you see this little J thing with a wand that looks worthy of Merlin? Do you see that? Okay, could you click on the Merlinian emblem? Are you able to see a choice of probability distributions?
Yeah.
Okay. Okay, ladies and gentlemen, we could have chosen any number of probability distributions. We can elect to choose whatever probability distribution we want to impose upon how long they remain here, within limits. I mean, we can't have one that has negative amount of time. They They can't leave before they come in. That would be problematic from a causal sense. But they can leave at from any non-negative probability distribution that doesn't admit negative numbers. So, ladies and gentlemen, with an agent-based model, we're not limited to, we're not constrained to, we are not straitjacketed to the memoryless assumption that afflicts stocks. Okay? We actually can choose our own probability distributions. So that was one point. And they have implications. It's not just the mean that matters. Okay, ladies and gentlemen, stochastics matter here. Okay, now, yes,
I
question.
have a question regarding the formula, the unit form.
Yes,
If we actually close the parentheses after the 2,
yes.
which that will multiply the remaining, does that make any difference?
So it's a good question. If we went like that,
Yeah.
it would have yielded the same result. Because this also will be from 0 up to twice 1 over this. And 1 over this is 1 divided by 0.02, which is 50. And so essentially it'll be a uniform from 0 to 100, because this uniformly distributed number is simply simply multiplied by this number, okay, which is 50. So it'll end up being uniform between 0 and 2. By contrast, if it was a nonlinear function of the uniform, like 1 over the uniform, it would be rather different. But in this case, it's linear, it's just multiplying by it. So good question. I hope that's a helpful answer. Yeah. Okay. So yes, we could have written that. And actually, from a software engineering perspective, I would prefer that. I think that's a little bit clearer about what's going on, maybe even something like that. But you can argue that. Okay, so ladies and gentlemen, the next question I had was the following. Suppose that we wanted to introduce heterogeneity. We actually did at one point introduce heterogeneity into this model. So we did side-by-side comparison version. Here we go. Boom. Here we go. Okay, and we had a side-by-side model which included a parameter for the person called sex. Fair enough, and we could make this chance of transitioning depend on the value of sex. Fair enough. So in other words, we could introduce heterogeneity, and I argue we didn't double the size of the model when we did so. Okay, so here's a question from this very take-home exercise, which is due tomorrow. Okay, ladies and gentlemen, so suppose we wanted to have another parameter. I'll put it in a different way. Suppose we wanted to have a parameter income, and it's a double precision value. Could we do that? You bet we could. Could we have this rate of going from susceptible to afflicted depend on some continuous way on this income? So like the higher the income it is, the less chance you have to be afflicted. Could you do that? Yeah, you bet you could. You bet you could. This is a conceptually continuous quantity. It varies in a sort of smooth way, a very fine-grained way from 0 to, what is it? I think at one point Bill Gates's wealth overflowed 64-bit representation. So he couldn't, his wealth couldn't be captured in integer dollars on a microprocessor of the time. But it wasn't widely reported in the news for some reason. But the point is, income can be very large, and we can capture it in as fine-grained as fashion as possible. Okay, so fair enough. We could capture someone with an income of, $1,232.35 or $32,350,232.22, right? It's as fine as a very, very fine characterization. It's continuous, essentially, modulo sort of discretization involved in representation. Okay, so suppose we want to do a similar thing up here. Suppose we want to do a similar thing here. How could we represent income here? Not very reasonably. What could we do? What sort of the...
We could make groups.
We can make groups. We can make categories. We could say, okay, there's afflicted for the lowest decile of income, meaning the lowest 10%, and then for the next one up, and then for the next one up. So we could turn it into categories. But we've done something that's a little bit unseemly from my perspective as a software developer. I start to get the willies, and sometimes it approaches the heebie-jeebies. When you start to modify the structure of a model just to capture characteristics of the data. And here we were talking about that earlier. We're taking a stock, for example, to secure a more appropriate distribution of times and dividing it up into several substocks just because we wanted a certain distribution in time for going from one end to the other. And here, taking the model and dividing it up and sort of replicating it for each income category just because it happens to be continuous and we want to capture, 20 categories or 10 categories. It's a little bit disconcerting to undertake an operation across the entire model, copy it just for that reason. So it's a little bit disconcerting, but that's about the best we can do without going to what? Does anyone know? This is represented by what's called an ordinary differential equation. And it's not ordinary because it's boring. I tell you, it is most certainly not boring, although some in the audience may choose to disagree. But it's to be contrasted with another type of differential equation that actually varies not only by time, by one independent variable, as this does, by time. It's an ordinary differential equation in time. But there's a different type of differential equation that can also continuously vary not only in time, but with respect to other variables. Does anyone know what that's called? Give you a hint. It begins with a P. Sorry? Partial differential equation, it's called. Now, you may think that that's a weird name because it suggests that it's somehow less whole than this. Far from it. A partial differential equation is referring to the fact you take partial derivatives. And I'm not going to go into that here, but basically, once you start representing these with a partial differential equation, you could characterize how this rate of transition here depends on a continuous income, for example, or continuous age. And it turns out that there's a reason that simulation frameworks like this don't typically represent that, because the handling of such differential equations is it's a much more specialized business. And there tends to be a lot of sort of needs to change how you represent it, how you handle it, depending on the particular characteristics of the differential equation you're dealing with. So ordinary differential equations are incomparably easier to work with from a standpoint of a general simulation package like this one. Partial differential equations tend to have a lot of specialized solver for elliptic equations or hyperbolic equations, etc. Anyway, so the short answer to this is, which is all that I'm looking for when you handed it in, or when you will hand it in, is that it's not easy, and basically you can't represent a continuous quantity in a fully continuous way in an aggregate model. Instead, ladies and gentlemen, you are representing categories that approximate it. By contrast, in an agent-based model, you can sure as heck represent a continuous quantity associated with each person. It's a very natural thing to do. Okay, final question. Hope you folks do well. Final question. How does the running time of a model, so we talked before about how running time, as you add in heterogeneity, as you add in these distinctions between people, how does that affect, like if I add in sex to, if I want to have this have a distinction between affliction hazards for men and women, how would I capture that? So, yeah, I make a copy, well, I could copy it here. So there'd be another pair of stocks with another flow between them. So it'd be susceptible female, afflicted female, becoming afflicted female, and then there'd be a corresponding one for males with all three of those. In short, you duplicate the model, right? Doubles the model size. Doubles the model running time, too. Suddenly, you have twice the number of equations to numerically integrate. Ladies and gentlemen, with an agent-based model, how would adding in sex change the running time of the model?
Very minimally.
Very minimally, if at all. I mean, you could get into, well, maybe the cache wasn't quite as effective and so on, but it's in the noise, basically, as far as, you know, a simple dichotomous thing there. It's a very minor effect, very, very minor compared to anything for aggregate. How if I add in a continuous quantity, a quantity with tons and tons of different possible values? How does that affect the running time?
Not really.
Yeah, it's basically minimal. By contrast, if I want to capture a bunch of different values of income categories here, maybe I copy this 20 times, so you capture 20 income categories. It sure is expensive. It's multiplied the running time by 10. Okay, so heterogeneity costs for aggregate models. And it's not too hard to imagine introducing enough heterogeneity where the running time of these models really, really slows down, where there's a lot of empty cells, situations where there's no one in this particular income and education and sex and ethnicity category, very, very sparse. Okay, but ladies and gentlemen, now let's flip it on its head. I want to ask a question of a different sort. Suppose we double the population size of the model. How does that change the running time of this model? The aggregate. It doesn't really. Why not?
Because it only has to change the calculations for susceptible, whatever susceptible.
Yeah. So look, computers don't run any slower. Within limits, they don't run any slower if you're dealing with computing equations involve larger numbers, right? 2,000 compared to 1,000, 10,000 compared to 1,000. Just numbers there. Count of people in susceptible, it's just a number, right? Count of people in afflicted, just a number. You double that number, it's not going to run slower in terms of performing a calculation. By contrast, in an agent-based model, how does the population size affect things? Does it affect it at all?
Yeah.
Big time. Big time. So you could even run, the population of 10,000 versus 1,000, and you will see the most pronounced of difficulties. As you raise the number of people in the population. Ladies and gentlemen, as you raise the number of people in the population, how would you expect the running time? Suppose you double the number of people in the population. How would you expect the running time of an agent-based model to be affected?
Probably double.
Okay.
Double, maybe a bit less, possibly a bit more.
Okay. A good answer. So you could argue it approximately doubles, and I'd agree in many cases. It could be more, it could be less. I mean, look, if a lot of the time running the model is just starting it up, getting it going, loading the data structures to memory and so on, it may not, and if you do it for one person versus two persons, it's probably going to make really small difference compared to that overall overhead. On the other hand, if you're dealing with 1,000,000 versus 500,000, it may make a really big difference. It'd be approximately twice the running time, because it's the running of the model that takes most of the time, not just loading it into memory. So you could argue in some cases it's less than double, but for decent sized models, it'll probably be at least double. Why could it be more than double? Why could it be more than double? You double the size, why could it take more than twice as long to run?
If agents are interacting with other agents,
Yeah.
it would be more.
Big,
Way more.
yeah. Now that is a really savvy answer, and we're going to be exploring that in minutes. as we introduce networks. So maybe each agent interacts with 10% of all other agents or 1% of all possible agents. You double the size, and now agents are having more connections as well per agent, and they're actually the model running time is going to go up in the limit with the square of the number of people, because each person is connected with a certain fraction of the other people. Okay, so that's a good reason. How about thinking back to 215? Oh, you people don't seem to want to think back to 215. Why would doubling it, why might that lead to more than a doubling of running time?
Might go past memory limits.
Might go past memory limit, starts hitting the disk, right? Starts paging out to disk of this, and then things really slow down, like grind to a slow crawl, which you probably experienced at one point in your life or another. So ladies and gentlemen, you can, if you get large enough, you can really start to run into memory constraints. They hit lower levels of the memory hierarchy, they go to disk, or it'll just do cache misses. It won't hit in the caches to get it from memory. And in short, doubling it may actually lead to more than twice as long running time. That's a big issue. It's a big issue. It's not a small issue. Any logic can run pretty comfortably up into the million, maybe up to 2 million range, and after that it starts to really bog down. Now, there's tricks you can do to speed it up, do it without visualization and so on, but you start to really run into memory issues, etc., and it costs. Okay? So ladies and gentlemen, big picture, heterogeneity, introducing heterogeneity makes what sort of model slower? Aggregate or agent-based? Yeah, system dynamics, aggregate models. We'll see later the system dynamics at an individual level too, but it's aggregate models. Doubling population size, as you increase that tends to make what sort of model slower? Agent-based, indeed, yeah. Okay, so ladies and gentlemen, let's build on our observations. Let us repair now to a new model. Ladies and gentlemen, now is the time where we will introduce agent-agent interaction. So, roll up your sleeves, start up your AnyLogics, and we will now compute. So, I'm going to pause the recording. I'm going to save the